miss your faces, guys. How are you? Please, everyone, unmute yourself. Okay. I hope your network is fine. How are we?
We're good, ma'am.
It's great. Okay. I put some videos on YouTube. I will share with you guys the link because I've realized that most of you guys have not been connected. So I will share with you a link that you can download from YouTube with a note starting from the weights up to where we are going to end. Let me hope the network won't cut us off. On your notifications or maybe on your on the lecture notes. So I try to copy up all the links and then put them up where you can download. Okay. So we went far up to now the end of station. So now we are going to start with the friction forces. Can you hear me nice? Or it's my maybe network, or is it fine?
It's fine. I can hear you.
Okay. Okay, so we have discussed about the forces. We said that if a body experiences an external force, so then the body is more likely to move. So one of the external forces that we are going to discuss today is the frictional force. Okay, so the friction force is a force which always tries to resist or tries to stop the object in motion. Okay, and the friction force is always parallel to the surface. Okay, so if you have an object, let me say it's placed horizontally on the surface, and this surface is friction. There is friction on this surface. So if you push, if you apply a force, let me say a pushing force, you are pushing this object in that direction. Then the friction force as this object moves, since this surface has friction, then there is a force opposing in the opposite directions of the applied force. Okay, so it's always parallel to the surface. So if it is placed horizontally like this, then it's always parallel on this direction. Okay, so yes. The one with the, do you have a question? Okay, so we have two types of
Frictional force.
frictions. Okay, so we have what we call kinetic or sliding friction, and we have what we call static friction. Okay, the kinetic or sliding friction, this is related to the movement. As you can see here, the name kinetic. Okay, so it means this force, the friction force, we likely normally denote it with Fk, appears when the object slides, like when the object moves. Then the object experience a kinetic friction. if the object is in motion, because that one is trying to resist, or it's trying to stop the object from moving. Okay, then we have another one that is called static friction, as I said. So this one is denoted with Fs. The static friction is a friction force which keeps the object at rest. Okay, so in other words, the static frictions, it's the friction on the surface in such a way that the object will not move. So whether you apply more force to this, you apply a force to an object, if the friction force of the surface is greater than the applied force, then your object will not move. So and these forces, okay, depends upon the nature. So it's like it depends on the surface and upon the degree to which they are placed together. Okay, so it depends on where it is placed. Like if you look up onto these two surfaces, okay, so if you look up on the first surface here, you can see that the buoy here, it's sliding. Okay, so this buoy is moving on that. So there is a friction force which is opposing that buoy. So we can say that the buoy is moving up in the horizontal surface. Okay, so your friction force is always in the opposite directions of your motions. So if you look up on this one, the flog is just resting upon that inclined surface. So you will see that the force, or the static friction force on the surface where the flog is more than the force that the flog is applying. That's why you can see that this flog is not moving. So this flog is just tenting, it's just at the rest, so it's not moving at all because of the friction force. Okay, so the magnitude of the frictional force is proportional to the normal force. So we have discussed about the normal force earlier in the notes. So which means that your frictional force depends on the normal force. If you increase the normal force, then your frictional force also increases. The magnitude of the frictions, okay, so remember we said that the forces are vectors. So their magnitude, Fs for static, and we have the Fk for the kinetic. Okay, so the static force, as I said, it varies, depends on the surface. Okay, it can range from 0 up to a maximum of mu s, the kinetic coefficient times the normal force. This is what we are talking about. So if you look up on this figure, we see that the frictional force, as you can see, keeps on increasing here until it reaches the maximum static force. So it means the static force, frictional force, depends. It can vary from 0 up to a maximum when is equal, at this point is equals to the mu s times normal force, while the kinetic friction is always constant. Remember we said that the kinetic friction is when the object is on motion. Okay, so the kinetic frictions of the surface is just one value given by equals to the mu k times the n. Where did mu k? This is what we call the coefficient of the kinetic friction. Okay, so the object of a given surface, okay, so when you have that mu k is less than the ms, then you have that the maximum or the frictional force on that surface is greater than the kinetic force. Okay, so remember and keep in note, as I've said, that the static force can be any values up to the mu s times n. Okay, so we just want to check the friction force versus the applied force. Okay, we just want to relate what happens. Okay, so we have that the frictional force at rest, when the object is at rest, then the magnitude of the static friction is equal to the applied force. Okay, when an applied force becomes large, who is that it is okay,
Miss
so
Nambinga,
yes,
can you just mute everyone?
okay.
Thank you.
I didn't want it to mute because it's always having discussions.
You can mute at one stage so that people can come in. Otherwise, we don't hear you. There's so much background noise.
Oh, okay.
Hey, Miss Nambinga.
Yes. Miss Nambinga is listening. Miss Nambinga is listening.
It's okay, Miss.
Yes, good. How are you?
Hi.
Tina, can you just mute yourself? It seems like you did something that I can't mute you.
Who's that, ma'am?
Tina or Sina.
Ma'am, mute me too.
It seems also I can't mute you. What did you do to yourself? You can mute yourself. Okay, where were we? Please don't unmute yourself, ne? Okay, so we were just saying Sina, can you please mute yourself? It seems you try to block me to mute you. Okay, so you have that when you apply a force, okay, when the applied force becomes larger, then you have that the friction force, I mean the static force, it equals to the maximum. Okay, and the object starts sliding. So the object normally starts sliding when you have a sliding friction, I mean a static friction force, which is equals to the mu s times the n. So once the object starts to slide, then a smaller force is required in order to keep an object moving at a constant velocity. Okay, so it means here we are only saying that what is required, we have that a normal, we require a friction force, a kinetic friction force, which is equals to the mu k times n, and we need a less frictional force, which is equals to the as we have like mu s times the normal force. So because we this time we have that the kinetic friction force is less than the normal, static coefficients. Okay, during sliding, if you have a force, if you apply more force than a frictional force, then your object will start to accelerate. Okay. Who is this? Okay, so during sliding, if you have an if the object starts to move and the applied force becomes lesser than the applied then the friction force, then the object will eventually stops, because as I said that the friction force, it always tries to oppose the motions. So if the friction force is larger than the applied force, if even if the object was moving, then the object will eventually start to stop. Okay, so if the block is pushed, okay, we have an example here. Let's say you are pushing a book, this is a physics book, on the table, then calculate a force. Tina, please.
Oh, if moya na re. Na ndi kuligie kujoin class ai.
Okay, so we have that okay, so if you look up on this example, what did I do now? So if you have look up on that example, you will see that. So you will see that Sina, can you please mute yourself? You are disturbing others, or else I will remove you. Okay, so if a book is pushed, then it calculates the force. So you can see that we have an applied force. Okay, so must calculate the force required to keep the book sliding at a constant speed. Okay, if the mass of the book is that one, you are given that the static coefficient is 0.84 and the kinetic force is equal to 0.75. So you will see up on this, as you can see from the free body diagram, as I've said, the free body diagram is used to show all the forces acting on that object. Okay, so as you can see, you apply a force which is going up on that direction. Okay, so we have a surface. Okay, so you have a surface and you have a book where this is the book placed on that surface. Okay, so then you apply a force. You are pushing a book in that direction. Okay, let me just put this force on this side. So this is the force that you are applying, and then there is a friction force which is opposing that force. Okay, then I say that we have a normal force which is always perpendicular to the surface, and the object always exert a weight to an object. Okay, so we have that these are the forces. So this object will move in that direction. Okay, so then if we apply the Newton's second law, it says that summation of all the forces, it equals to a mass times what? Times the acceleration. This is what we said. Okay, and then we say, remember this is acting in two different directions. You don't sum up all these forces here because they are acting up on the, so we have the forces that are acting in the x direction, and we have the forces that are acting on the y directions. So if we look up on the y direction, let's say the upward, our directions goes like that. I always say it's always important for you to indicate which one is your direction, which one is your positive y, and which one is your positive x. Okay, so if we look up into a direction of y, we say that the upward is our positive direction. Then we have that a normal force, which is positive, minus the weight, it equals to 0. Why is it equals to 0? There is no acceleration in y. We don't have the acceleration in the y direction. That's why we have a normal force, which is equals to normal force minus the weight is equals to 0. So if we solve for a normal force, then we have that a normal force is equals to the weight. And we know how to calculate the weight. We know that the weight is equals to mass times what? Gravitational acceleration. Okay, so this is what we have on the y directions. And then we move on the x direction, because the x direction is the one that will help us to find the force, the frictional force, the maximum maximum force required to do what? To keep the body, okay, to keep the book sliding at a constant speed. Okay, so in the x direction, we say that this direction is our positive. Then we have that a normal, the applied force minus the friction force, it's equals to the, okay, is this book moving or not moving? Okay, so it's equals to, calculate the force needs to keep the book sliding at a maximum force. Okay, we don't even need to go up on that because we are given that. Okay, so we have a mass. Okay, so if we have to do that, then this is the mass times the acceleration. Okay, so we don't know what the acceleration is, we don't know what the friction force is. So but the question is not even asking us to find what is the acceleration or whatsoever. It's only asking us to find the friction force required to keep the book sliding with a constant speed. Okay, so we have that the friction force, remember from what we have from our notes, it says friction force is equals to the coefficients, and this is the kinetic. This book is moving. It says what is the force required to keep it moving on the with a constant speed. Okay, so it means we have the kinetic friction. So we have that the kinetic coefficient times what? Times the normal force. And what is our normal force? Our normal force is equals to the weight, okay, which is equal to the mass times the gravitational acceleration. So we have that a normal force, mu k, times the mass times the gravitational accelerations. We know all that. We know what is mu k from our question. It says that our mu k, it equals to 0.75. Okay, so and our mass is equals to the 1 kilogram. Okay, so this one we put in our values. What is our mu k? Our mu k is 0.75. And what is our mass? Our mass is 1 kilogram. And what is our gravitational acceleration? It's always important to see what is given. Let's say here we are using 9.81. So if we put in those values, so 0.75 times 1 times that value, and then we have something like 7 points, something like 7.3. Okay, so we have something like 7.3 Newton. So this one is the maximum force. So this is the frictional force. Remember we say that if the object is moving, then it requires a frictional kinetic force which is trying to oppose that movement, that motion, that object in motion. It's trying to stop it. Okay, so if the applied force is greater than the frictional force, okay, then the object keeps on moving. It will keep on motion. So this one, the example is saying, in order for this object to keep on moving at a constant rate, which means that the applied force should be greater than the frictional force. You can just try to test it. Okay, if you could knew what the acceleration is, we can try to test it. Okay, but let me say if this force, let me say the acceleration, it's always less than the, it's always less than the force of the gravity. Let me say the acceleration is equals to 2. Okay, then from this equation of the on the x direction, we have that force minus the friction force, it's equals to the mass of an object times the acceleration. If, let me say, if this object is accelerating with 2, okay, then we have that force, it's equals to the mass times the acceleration plus the friction force. Even without values, you can already see from here, from this equation, that there is an amount of forces which is added to the frictional force, which is equals to the applied force. So here you can already tell that the applied force is greater than the what? The friction force. Okay, so that's what is important. Okay, then in example 2, let's say a box of a weight, you're given a weight, is at a rest. Okay, so it means the box is not moving. With static coefficient equals to 0.3. A rope is attached. Okay, you have a rope which is attached and pulled horizontally with a tension equals to 30 Newton. Which way does the box move? Go play outside. Okay, so if you have that, you are given a box. Okay, you have a box. Okay, and you attach a rope with a force, tension force. We said that the force associated with the rope is called a tension force, equals to 30 Newton. Okay, and there is a friction force on this surface. Okay, so there is a static friction force with a static coefficient equals to 0.3. Okay, then now if you apply a force, now the question is asking in which direction will the body move. Okay, so the moment that body starts to move, then we say that you have a maximum static coefficient on the object. Okay, so in order for you, as I said, this type of the equations, you just can't say, you can't just say it will move into a positive or negative directions. I always say that you always have to work out. Okay, so if we do this, there is always a normal force, which is always perpendicular, and there is always a weight force. Okay, doing the same thing that you were doing, summing up all the forces acting in each direction, we have that in the y direction, we have a normal force minus the weight is equals to 0. This object is not moving. Okay, so here we have that a normal force is equals to the weight. Okay, on the x direction, we have that a tension force minus the friction force equals to the mass times the acceleration. Okay, but we don't even need to go there. All we need is to calculate what is the friction force. If this surface has a static coefficient, which means the force which is opposing or which is preventing the box from moving. Remember, we say that is equals to the coefficient times the normal force. Okay, our normal force is equal to the weight, which is equal to the mg. So we are given that this is equal to the mu s times the normal force, which is equal to the mass times the gravitational acceleration. Okay, we know what the coefficient is. We know what the mass of the box is. Okay, so we are given the weight, so we know what the weight is, we know what the coefficient is, so we can simply calculate what is the friction force required. Okay, so this one is simply the weight that we are putting up. So given that a weight is 50 Newton, then you multiply that with the static coefficient of 0.3 or 0.03. Let me check on the question. 0.3. Okay, so if we multiply that, we are getting something like 15. Okay, so we get that our friction force, the static friction force, is equals to 15. So we can see that the applied force here, the tension, which is the applied force, which is equal to the tension, is greater than the sliding or the static force. So therefore, since the static force is less than this object, the force applied to the object, then this object will start to slide. In which direction? It will start to slide on the direction of the net force. So this object will start to slide in that direction. So it will go to the right side or whatever positive side. I don't know how you want to describe it, but as long as you do something like that. So it depends if you say this is right, this is left, or you say this is positive, this is negative. Whatever description you use, it's fine. So since you can see from our calculator, we have that the friction force, static force, is less than the coefficient, I mean the applied force, then that thing will start to slide on the same direction as the net force. Okay, let's check up on when you have a force. If you have placed an object on the incline. Okay, so you have a 1.0 block is placed on that at a 25-degree with the horizontal. This is very, very important, with the horizontal. What is the force of a static friction? Okay, which means what is the force required by that block so that it will not accelerate, it will not move. Okay, another one is what is the static coefficients. Okay, so remember we said that the normal force is should always be perpendicular to it's always perpendicular to the surface. So if this is your surface and you place up your block, okay, and it says it makes up an angle with the horizontal, which is equals to 25 degree. Okay, so this force will exert, the object will exert a weight. This one is always a must. There is a weight going, the force due to the gravitational acceleration, and we have a perpendicular force, which is the normal force. It's in that direction. So as I've said, in the normal force, when you have a case where there's a perpendicular, there should be a force which is acting on the vertical component, which is opposing that normal force. Okay, so if we have up, then that force is what? It's the weight. As you can see that your weight is acting in angles, so it's the weight in which direction? In the y direction. And we have a weight which is acting in the x direction. Because remember, you can see that your weight is acting in components. So it's acting on both x and y. Okay, so we have that one here. So we have a frictional force which is opposing that motion. Okay, so we have a static, because they are saying what is the static means for that object not to move. Okay, very important for us to choose our directions. I can say, okay, this direction here, it's my positive x-axis, and my upward, it's my positive y-axis. Okay, so like in this, my drawing is not that good, but this one, the one which is on the vertical, it's my y, this one, and the one like this, it's my x. This is my y, and this is my x. Okay, so we do the same thing. So you are asked to find what? You are asked to find the normal of the static coefficients. The static force and the static coefficients. Remember, we say that the static force is equals to the static coefficient times what? Times the normal force. And what is the normal force? The normal force at this case, if we apply the Newton's second law, a normal force is equals to the weight which is acting in what? In y. Okay, and this is our theta. This is the same theta. This is the same angle here, just the rotation. Okay, so if we do that, what is our weight in y? Our weight in y is equals to what? If this is our angle, now these ones become, this is the same as weight in x. Okay, So what is our weight in y? Go back to those to the Sohaka Tower stories, and this one becomes our adjacent, and this one become our opposites. Okay, so it means our weight in y, it's now equals to the weight times cos of an angle, while the weight in x, it equals to the weight in x, it's equals to the weight times sine of an angle. Okay, so it means our weight in y is equals to the weight times what? Times the sine. Okay, is equals to the weight times the cos of an angle. Okay, so it means our normal force is equals to that. So it means our static force is equals to. Okay, so here it can't help us because we don't know what is our force, static coefficient. So we go and make use again now of the diagram in the x direction. So in the x direction, we have that the weight acting in the x direction, it equals to, or let me say a minus, okay, a friction static force. And remember, this is static, it's not moving, so it's equals to 0. Since it's not moving, there is no acceleration, which means your friction static, it's going to be equals to the weight in x. So we know all these values. So your weight in x, you simply substitute what we got there, which is the weight times the cos of an angle, not cosine. So your weight, the static force is equals to the weight in x, which is equals to the weight times the sine of an angle. Okay, so means we got that our static force is equals to the weight times the sine of an angle. This is what we got. So we know what our weight is. We can calculate it. We are given a mass of 1. We know the gravitational acceleration, and we know what the angle is. So by doing that, we get that our weight is equals, our static force is equals to 4.1. Okay, so if we plug in all those things, we know a 1 times a 9.8 times a sine of an angle 25. So we got something equals to a 4.1 Newton. Okay, then the question again is asking us to find the static coefficient. So we know that the static coefficient is equals to the the static coefficient times the what? Times the normal force. So we know we can either calculate what the normal force is, or you can simply do, okay, my static force is equals to the weight times what? Times the sine of an angle theta. And what is my normal force? Your normal force, because from here you get that a normal force is what? From what we have that a normal force is equals to the weight times a cosine of an angle theta. So the weight cancels out. Then you simply left with sine theta over cos theta, which is equals to a tan theta. Okay, so here we just plug in the tan of an angle 25. 5 degrees. Or what you can do, you can calculate what is the normal force. Okay, remember, you know that the normal force is equal to the weight times what? Times the cosine of an angle theta. Okay, so then the weight here we can do, okay, weight is equal to the mass times the gravitational force times the cosine of theta. You plug in 1 times 9.8 times cos of the angle 25. What is my normal force? Okay, you get the value there. Okay, then you go on to the same calculation. You go on now to your equation and say static friction is equals to the kinetic, the static force times the normal force. So you have, you have that static coefficient is equals to the friction static divided by the normal force. Remember, you have found what is your static coefficient for, your frictional static friction, which is equals to 4.1. You found your normal force from here, you plug it in there, and then you get the answer. That answer will be the same as the one that we did. Like you see, that's the angles. Okay, so come there, come back. So we got that our kinetic, it's equal, our coefficient is equals to 0.46. Okay, so now I'll allow you to ask questions if you have questions. You can ask questions if you have questions. You can just even unmute yourself. You have questions? Or should we continue?
Miss, could you please just repeat question 3 a little bit?
Repeat the question 3.
Yes.
No.
Okay. Any more questions?
Miss,
Mm-hmm.
is the rerun of test 3 optional?
I don't know. Unless I have to find out from my...
Please find out, because we have so much pressure. We will be writing like test for the whole of next week.
Isn't it the test tomorrow?
Yes, it's apparently tomorrow.
Okay.
But we have to prepare for the test. We have a lot of tests that will be like for the whole week next week.
Okay. Any questions? Okay, now let's do questions related to what we are doing if you have questions. Huh? I don't know questions. Should I continue? Regarding the test, I will find
Yes,
out.
you can continue.
So I can continue.
Yes.
Okay. Okay, so we have another force which actually doesn't play much a role on our work. Like for us, we are actually not going to look much into this, but this force is called drag force or the air resistance. Okay. So what we have been doing it without the air resistance. Okay, so the air resistance is a special case of the friction force act upon an object as they travel through the air mostly. So it's like when you have an object falling, let me say if it is on the air, if it is falling, then there is always a drag force which is trying to oppose that object not to move up, like not to move down. Okay, so and mostly like you can see if you swim, mostly for those who knows how to swim, they can mostly this is the force which is helping you not to go under. Okay, because there is always a force which is above you, which is always trying to oppose the what the movement. Okay, so the force of the fruit, it acts mostly on the fruit, and that is called a drag force or the air resistance. Okay, this one it's the same as like the friction force. It's always oppose the directions of the motions. Okay, so the drag force depends on the size, how big, depends on the speed, how much it's falling with, it depends so on many things like the density, the liquids, the shape, and all those things. Okay, so you mostly in all your problems that you are doing, you neglect the air resistance unless you are told that there is a presence of the air resistance. Okay, so the effect of the air resistance on the falling object, like for the example here you have an apple. So you can see that there's a force of gravity, the weight, is it's the pulling down, because as you can see here, this object is falling due to the gravitational acceleration. Then this small, the purple one here, it's now the air resistance which is trying to oppose this force. Okay, so the net force on that is equal to the force of, as I said, you simply do the summation when you're calculating the net force. You simply do the summation of the air resistance, of all the forces acting on that body on the same directions. You don't mix them up. Okay, so with the friction, as I've said, without frictions, I think most of the work cannot be done. Okay, it's because of the friction when you are sitting, you are not falling. It's because of the friction that help us to walk. It's because of the friction that you're actually able to do so many things. Okay, so we come to the end of that, and the examples, summary questions here that you can go through. Like if you look up into question 3, it's mostly what was almost in your tutorial 3, and this is almost what we did with the example on the station when we were doing the station. Okay, this is simply the actual machine examples. Most of these questions are more likely like what you had on your tutorials. Okay, so do you want us to continue to a circular motions, or do you want to go and study for your test?
Ms. Nambinga,
Yes.
maybe we can end here.
Mm-hmm.
But I just want to say again, if you can please find out if that rerun is a must. If I don't want to rewrite the test, can I just retain my other amount?
Okay, let me just try to see if I'll get hold of her.
Okay.
Um, let me just check if she's online. from Michael. It seems her number is not here. What happens? Um,
Thank you.
all right.